All right, good morning, everybody, Physics 4DS students. Before I begin the lesson on Coulomb's law with electrostatics, I just want to draw your attention to the Microsoft Teams platform that we're going to be using for the remainder of the school year. So you have all been provided with an Office 365 login. You would have logged in with the initial password, spring 2020. And then you would have changed your passwords. You should all be able to log in. You will locate the Physics 4DS team. And you'll notice at the top that there are different tabs. So two important tabs are the files. Well, the posts are important. You'll see anything that I post, like assignments, will come up. But posts, yes, but files and assignments themselves. So the files, if we click on it, is where you are going to find the notes. So when you click on the Files tab, it takes you to the first folder called Course Materials. If you click on Course Materials, you'll notice that there are some units. So the unit that we are on right now, we just started, is the electric and magnetic fields. So if you click on that, you will then see all the notes that you need. So it's pretty straightforward now. For example, for today's lesson, you'll need Coulomb's law notes. So you would click on that and it should download it for you. So that's how you would access the notes. To access the assignments as a student, you click on the Assignments tab and it should show the different assignments. So then you would just click on, for example, the Conservation of Energy Concept Check or the Work and Energy Unit Assessment. So as the assignments come up, you can access them here, or you can also access them through the posts. So for example, Work and Energy Assessment and Conservation of Energy Concept Check. So I hope that kind of gives you a quick little overview of the Microsoft Teams, and let's begin the lesson on Coulomb's law. So this unit is the electric fields unit along with magnetism. This builds on what we did in grade 11 physics. So I've given you some bullets here of review topics. So you should be aware of the following points. The basis of electric charge, which we covered in grade 11. We're not really going to worry about milliken, so don't worry about milliken, but the elementary charge, again, E, is 1.602 times 10 to the negative 19 coulombs of charge. That's the elementary charge, the basis of all electric charge. Here's the law of electric charges, attraction, repulsion. How do we charge objects, friction, induction, and conductors and insulators. So review your Physics 3DS notes, but we are talking about electric fields. And there are two types of electricity. Non-moving charges and moving charges. Remember, Q is a symbol for charge. So non-moving charges are, the study is known as electrostatics. Okay, and then we have moving charges, which is current electricity. Okay, so again, you should review your Physics 30S notes. So we're going to jump right in and get going here. And we're going to begin our first look at electrostatics, and that is the concept of FE, which is electric force, electrostatic force. So here we refer to Coulomb's law. So Charles Augustin de Coulomb, the French physicist, and he worked on a series of experiments and determined examined the electric forces that existed between charged objects, and he came up with a law that quantified the amount of electric force. So when we're talking about charged objects, you refer to them as a point charge. That means that their diameter d is much smaller than the separation r between the charges. Note r in this case is not the radius. So if we have point charge number 1, so we'll call it Q1, and Q1 is separated from Q2, and the charge is irrelevant, but this distance, separation distance, is known as, or is given the symbol little r. So yes, that can be confusing because you think r is a radius. In this case, r is the separation distance. So his law states this: the electric force between two charged objects is equal to some constant k times Q1 times Q2 divided by the square of the distance. So this is Coulomb's law. Note that the electric force is directly proportional to Q1. The electric force is directly proportional to Q2. And force is proportional to 1 over the square of the distance. And then in this case, we refer to it as an inverse square law. K is Coulomb's constant. Okay, that's the name of it. And so you need to know this number. K is 9.0 times 10 to the power of 9 Newton meters squared per Coulomb squared. So that is the value of K. Again, you'll find that as well in your textbook. Okay, but Coulomb's constant is 9 times 10 to the power of 9 Newton meters squared per Coulomb squared. All right. So moving on. We can look at the comparative use of Coulomb's law. This is simply proportionality. If we look at it here, in this case, this is just looking at the relationship between the size of the electric force and the how it's affected by the different constraints, namely the charge size and the separation distance. Okay, so if we know the force Fe is 4.5 times 10 to the minus 4 newtons, what is the new force going to be if we make these changes? So what if we take the distance and we triple it? So the distance between Q1 and Q2 goes from R to 3R. Well, we know that F is proportional to 1 over R squared. So that means F is proportional to 1 over 3 squared, which means F is proportional now to 1 over 9R. So by increasing R by a factor of 3, by tripling it, the force is now going to be reduced by a factor of 9. So the new force will be 1/9 times the old force. So 1/9 times 4.5 times 10 to the minus 4 newtons, and we get our value. Again, remember the second function, EE, is how we do the scientific notation. So we would go 4.5 times 10 to the minus 4 divided by 9, right? 1/9 is the same as dividing by 9. And you get 5 times 10 to the minus 5 newtons. 5 times 10 to the minus 5 newtons. That would be the new force. This is just based on proportion. Second, what happens if we triple one charge but half the other? So that's 1 over 2, triple is times 3. So F was 4.5 times 10 to the minus 4 newtons. We want to know what's the new force. Well, we know that force is proportional to Q times Q. So force is now going to be proportional to 3Q times 1/2 Q, which means F is proportional to 3 times 1/2, or 3/2 Q squared. So there's our factor, 3/2. So F new will equal 3/2 times F. So 3/2 times 4.5 times 10 to the minus 4 newtons. So 4.5 times 10 to the minus 4 newtons times 3 divided by 2. And you get 6.75 times 10 to the minus 4 newtons. 6.75 times 10 to the minus 4 newtons. That is the new force acting on the object. Again, this is just proportions. Okay? So you only use this if you're given the force. You're not given anything else, and you're told, okay, comparatively, what's happening. In this case, we triple the distance, we change the charge, tripling one and having the other. So the third thing here is what happens if we do A and B simultaneously. So what happens if we triple the distance? So we go from R to 3R, and QQ goes to 3Q times 1/2 Q. Sorry, R squared goes to 3R squared, which becomes 9R squared and 3/2 Q squared. Okay, so F new is going to equal, okay, so again, we do our proportions. F is proportional to 1/R squared, which means F is proportional to 1/9R squared. F is proportional to QQ, so F is proportional to 3Q times 1/2 Q, which gives us F proportional to 3/2 Q squared. Okay, so our factor now is going to be 1/9 times 3/2, which is 3/18. And again, you can reduce to make it simpler. 3/18 is 1/6. So the new force is going to be 1/6 the value of the old force. So 1/6 times F, or 1/6 times 4.5 times 10 to the minus 4 newtons. And our new force is 4.5 times 10 to the minus 6. Oh, sorry, 10 to the minus 4 divided by 6. And you get 7.5 times 10 to the minus 5 newtons. 7.5 times 10 to the minus 5 newtons. Again, this is just proportions, so don't stress too much. This is just proportions of the values. What we really are going to explore now is how to calculate and use how to calculate electric force using Coulomb's law. But it's worth noting here, okay, the effect of the different variables in Coulomb's law. F is proportional to Q and Q, and F is proportional to 1/R squared. Okay, so how do we calculate Coulomb's law? So this is sort of the big piece here. We obviously have to use Coulomb's law. So Fe is K times Q1 times Q2 divided by R squared. So yes, there's some calculations that you're going to have to do. We know K is a constant, so we know K is 9.0 times 10 to the 9 Newton meters squared per Coulomb squared. Again, units are there, but that's the value we need. So we need to know Q in coulombs and R in meters. So a coulomb is a large amount of charge. So typically we work with smaller amounts. And so we've got the micro. And again, getting the course, we talked about what micro was. So micro was 10 to the minus 6. So 1 microcoulomb would be 1 times 10 to the minus 6 coulombs, for example. So we have this. Two charges are both equal to plus 5 microcoulombs. So Q1 equals Q2 because they're both the same, which equals plus 5 times 10 to the minus 6 coulombs. That is the value of each charge. They're separated by a distance r of 0.75 meters. What is the force that exists? So we simply set up Coulomb's law. Fe equals K, so 9.0 times 10 to the 9 Newton meters squared per Coulomb squared, times Q1 times Q2. In this case, they're both the same, so we can just square Q times Q. So we would go 5 times 10 to the minus 6 coulombs squared, divided by r squared, 0.75 meters squared. So now there's a lot of calculations. It seems it's not too bad, plug and chug. I would highly recommend you do this all in one step if you can. So 9 times 10 to the power of 9 times 5 times 10 to the power of negative 6 squared. And then we'll divide that by, in brackets, 0.75 squared. And you get 0.4. The force would be 0.4 newtons. So that would be the size of the force that exists between the two charges. So here, if we look at a diagram, you get a picture. Q1, Q2, separated by 0.75 meters, and they're both plus 5 microcoulombs. The force that exists between them would equal 0.4 newtons. And again, if we did a free body diagram, because they're both like charges, positive, Q1 will push Q2 to the right, and Q2 will push Q1 to the left. So this would be the force of Q1 on 2, and this would be the force of Q2 on 1. And note that this would be a repulsive force. So how do we indicate a repulsive force? Use a plus sign. So for electrostatics, a plus sign indicates it's repulsive. A negative sign would indicate that it's attractive, and they would move towards each other. So just make sure you note that. Okay, using Coulomb's law to calculate an unknown charge. So a positively charged particle, x to the power of plus 6, x plus 6 means plus 6 elementary charges, which is 6 times 1.602 times 10 to the negative 19 coulombs. Remember, E is the elementary charge, 1.602 times 10 to the negative 19 coulombs. So we need to get our Coulomb charge right off the bat. So 6 times 1.602 times 10 to the negative 19, and we get 9.612 times 10 to the negative 19. Okay, there we go. The positively charged particle experiences an attractive force towards an unknown charge. So x plus 6 is attracted towards this unknown charge. So if this is positive and it's attractive, the unknown charge must be negative. So Fe is going to be attractive. Okay. So we know that this unknown charge is going to be a negative Q. What is the magnitude of the unknown charge? So this is the matter of, again, using Coulomb's law and solving for a different variable other than Fe. So we've got Fe equals K Q1 Q2 over R squared. So 1.5 times 10 to the minus 3 equals K. 9 times 10 to the 9 times Q1, which we calculated here, times 9.612 times 10 to the negative 19 times Q2 is our unknown, divided by R squared, 0.65 meters. I'm not using units, so I won't write them here either. Squared. You should always write units, but I don't have a lot of space. So now how do you solve for Q2? Well, we just move the variables around. We square the 0.65, we multiply it over, and then divide it by the product of those two numbers. So I can do that all in one step. And we know Q2 has to be a negative number because it is attracting the positive charge. So regardless of if we get a positive or negative number, we know Q2 is negative. Okay, so we'll take 1.5 times 10 to the power of negative 3 times it by 0.65 squared and divide by 9 times 10 to the power of 9 times 9.612 times 10 to the power of negative 19. And we should get our Q2, okay? And that is a large charge, and we get that. So we get 7.3259 times 10 to the power of 4. So 73,259. So 73259. Okay, and we get our charge that way. So Q2 equals negative. How many sig figs? 2. Negative 73,000 coulombs. Okay. Again, we can use Coulomb's law to solve for Q, Q, or R if you want it. All right. Let's talk about the vector nature of Coulomb's law. So the vector nature of Coulomb's law, okay, talks about when we have multiple charge systems, not just two. So Coulomb's law gives us the force between two charges. So what if we have more than two? In this case, we've got 4. We've got QA, QB, QC, and QD. So what we can do here is pick a charge and find out the total force that's acting on it. In this case, we're going to calculate the total force acting on charge. Where are we? Calculate the total force on charge B. Okay, so we're going to calculate the total charge on charge B. Total force acting on charge B. Alrighty, so if we look here, charge B is right there. We draw a free body diagram. So there's 3 charges that are affecting B. Charge A, charge C, and charge D. So charge B is positive. So let's look at AB. So A is going to repel B. So that's going to be to the right. So the vector arrow, this would be the force of charge A and charge B. So FAB. Charge C is negative, and charge B is positive. So charge C is going to attract the charge B. So the force is also going to be to the right because charge C is going to pull pull charge B towards it. So there'll be a second force going to the right, and that would be the force of charge C on charge B. And last but not least, we have charge D here. Charge D is positive. Charge B is positive. So charge D is going to push charge B to the left, repelling it. So that would be the force of charge B on charge B. So we need to know these three forces, and then we can get a total to get the total force. F net on charge B would equal force of charge D on B plus force of charge A on B plus the force of charge C on B. So how do we get those three forces? Coulomb's law, and then we would add them up. We're going to say to the right is positive direction, and we'll say to the left is the negative direction. Okay, so you could even go so far as to say negative charge, negative FBD. So a couple things. This is milli, not micro. Okay, so milli means 1 over 1,000. Okay, or 1 times 10 to the minus 3. So these are all millicoulombs, and we have micrometers. So these micrometers means 10 to the minus 6. So we know the distance between A and B is 9, B and C is 8. But how do we get the distance between D and B? You have to add the 8 and the 6 to get 14 micrometers. Okay, so we've broken this down. We'll use Coulomb's law 3 times to get the F total. So FAB will equal KQA QB over RAB. That's the distance between the two squared. So that's 9 times, I won't write units just to make this go a bit faster. So 9 times 10 to the 9, okay, multiplied by, all right, so QA and B. So A is 5 millicoulombs and B is 3 millicoulombs. 5 times 10 to the minus 3 times 3 times 10 to the minus 3 divided by the distance between them squared. The distance between A and B is 9 micrometers, or 9 times 10 to the minus 6. So that would be 9 times 10 to the minus 6 squared. Okay, and we'll get a number. And we know that it's going to be in the positive direction. Come back and do the plug and chug after. Let's find C, the force of charge C on charge B. So FCB will equal K times QC QB over RCB squared. So that's going to equal 9 times 10 to the 9. QC and QB. So QB, we already know is 3 millicoulombs, C is 2. So 3 times 10 to the minus 3 coulombs times 2 times 10 to the minus 3 coulombs divided by the distance squared. So CB is 8 micrometers. 8 times 10 to the minus 6 squared. And that's also going to be to the right, so positive. So FD on B is going to equal K, so 9 times 10 to 9 times QD. So in this case, D is 4 millicoulombs and B is 3. And we add up the two distances to get 14 micrometers. Get 4 times 10 to the minus 3 times 3 10 to the minus 3 divided by 14 times 10 to the minus 6 squared, and that's going to be to the left, so that's going to be negative. Okay, now we'll plug and chug. Again, you want to try to do this all in one step. Okay. So we get the first force, 9 times 10 to the 9 times 5 times 10 to the minus 3 times 3 minus 3 And then you divide that. Oh, I just deleted it. Okay, one more time. 9 times 10 to the power of 9 times 5 times 10 to the minus 3 times 3 times 10 to the minus 3. Bracket that equals divided by 9 times 10 to the minus 6 squared. And you get 1.666 repeating, so 1.67 times 10 to the power of 15. 1.67 times 10 to the power of 15 newtons. Calculation here. I do. 6, no, we're all good. Okay. Second force. Nine times 10 to the power of 9 times 3 times 10 to the power of negative 3 and times 2 times 10 to the power of negative 3. And then we divide that by 8 times 10 to the power of negative 6 squared. You get 8.44 times 10 to the power of 14. Newtons. And last but not least, the third force, 9 times 10 to the power of 9 times 4 times 10 to the power of negative 3 times 3 e negative 3 divided by 14 times 10 to the power of negative 6 squared. And we get 5.51 times 10 to the power of 14. Okay, so we got the three forces, and now we just need to add them up. So F, the total force will be first force plus the second plus the third. F net will equal 1.67 times 10 to the power of 15 added to 8.44 times 10 to the power of 14, and we add 5.51 times 10 to the power of 14, and you get 3.065 times 10 to 15. Now it's positive, so F net will equal positive. Okay, and we'll take it to 3 sig fig, so 3.07. Whoops. Remember, we can round down. 3.07 times 10 to the power of 15 newtons. That would be the F net on charge B. Now, we could find the F net on any charge, A, B, C, or D, but this example, we found the F net on charge B. Remember the rounding? An even number followed by a 5, you round down. If it's odd followed by a 5, you round up. So the answer is 3.07 times 10 to 15 newtons, and it's to the right, obviously, positive direction. So that is the vector nature of Newton's law, of the Coulomb's law. And so it should be no surprise then that we can do two-dimensional. So this would just be, again, adding 2D vectors. So just a recap, the vector nature of Coulomb's law. Step 1, find all forces using Coulomb's law. Step 2, add them. I don't know, that's really straightforward, but you gotta break it down. So however many charges there are, find the individual forces through Coulomb's law, and then you add them all up, making sure you keep keeping track of your directions. Okay, so if it's two-dimensional then of course we have to deal with Newton's, we have to deal with adding 2D vectors. So vector resolution. So let's take a look. Calculate the total force on charge C. So we want F net on charge C. So charge C is right here. What I would do is I would draw a free body diagram. So there's charge C. Charge C is positive. Charge A is directly above it, it's negative. And charge B is up to the left, and it's also negative. So it should be pretty obvious that there'll be an attractive force between A and C, and an attractive force between B and C. And B and C is separated by a distance. We'll call that R3. Okay, and so because this is directly below, we'll assume a right triangle, so we can figure out the angles after. So if we draw a free body diagram, the force of A on C is going to be due north. And the force of B and C, well, it's going to pull it up into the north and to the west. So that would be the force of B on C. Notice we have two vectors, and they are two-dimensional. Now, we're going to find FAC and FBC using Coulomb's law, and then we'll have to come back and do the vector components. So first thing that I would do is find the two Coulomb forces. So let's figure that out. FAC, okay, and FBC. But to do that, we need to know this radius. Okay, so we've got a triangle. R1 is 12, R2 is 20, so we need R3. So A squared plus B squared equals C squared. 12 squared plus 20 squared, and then you square root. You get 23.32. 23.32. And this is centimeters, so we got to divide to get the meters. So 0.12 meters, 0.20 meters, and 0.23 meters. We'll keep it all to two decimal places. Okay, so FAC will equal K, 9 times 10 to the 9, times QA. So that's 5 microcoulombs, so 5 times 10 to the minus 6, times QC, 3 times 10 to the minus 6, divided by the distance, which is 0.2 meters, 0.2 squared. Okay, and we know it's going to go due north. Nine times 10 to the power of 9 times 5 times 10 to the minus 6 times 3 times 10 to the minus 6 divided by 0.2 squared, and you get 3.375. 3.375 newtons. That's the force of A on C. So 3.375 newtons due north. If we're looking at a top view, the force of BC will equal the constant K, 9 times 10 to the 9. QB is 3 microcoulombs. So 3 times 10 to the minus 6 times QC, which is also 3 microcoulombs. 3 times 10 to the minus 6 divided by the distance we just found, 0.23 squared. Okay, so 9 times 10 to the power of 9 times 3 times 10 to the power of negative 6 times 3 times 10 to the power of negative 6. Whoops. Times 10 to the power of negative 6. And we divide that by 0.23 squared. 1.53. We'll go 1.531. 1.531 newtons. Now we need a direction. So how do we get this direction? We know it's going to be theta degrees north of west. So how do we get this angle here? Okay, we need to find this angle there. Again, two parallel lines, transversal, alternate interior. So we need theta. Okay, so we know our three sides of the triangle. We want this theta here. So we have opposite over adjacent. So inverse tan, 20 over 12 is our theta. Make sure the calculator is in degree mode. Inverse tan. 20 over 12. And you get 59 degrees north of west. So 1.531 newtons west, 59 degrees north. Okay, now we've got to add these two vectors. So this is north, F1, FAC is north, and FBC is that 2D. So we're going to make our table. Vector X, Y. So we've got FAB, we've got FCB, and then we've got FNet. Okay. This should go pretty quick because we've done this before. This is just 2D vectors. Again, I'll draw them to make it a bit easier for us. Okay. So FAB is going due north, and FCB is going north of west. So we've got X, FX, and we've got our FY. And that's FCB. Okay, so FAB has a 0x component, and its y is north, so it's positive 3.375. So that's north is positive. So positive 3.375. FCB. So our theta is here. So our x is going to the left, so it's negative, and our y is going up north, so it's positive. X is adjacent, so it's going to be cos. So the x component will be negative 1.531 times cos 59. And the Fy will be positive 1.531 sine 59. Now we can get our Fnet. So our total x will be 0 plus, we know it's negative, so it's going to be 0 minus 1.531 cos 59. So negative 0.785. So negative 0.7885. So that's going to the west. And now we can add up the y. 3.375 plus 1.531 sine 59. You get 4.687 positive. Positive 4.687, which means it's going north. So now to get our total, we do our total final triangle. So x is going to the left, fx. Y is going north, fy. And that's our Fnet on charge B, and there's our theta. So Fnet B, A squared plus B squared equals C squared. So square root 0.7885 squared plus 4.687 squared. And our angle, theta inverse tan opposite 0.7, whoops, nope, 4.687 over 0.7885. And we can figure out our numbers. So we'll get our magnitude first, 0.7885 squared plus 4.687 squared. Square root that. 4.753. Okay, so 4.753 newtons. And our angle inverse tan, 4.687 divided by 0.7885, 80 degrees. That's north of west. So our final answer to sig figs is 2 sig figs F, and that's charge B, equals 4.8 newtons west, 80 degrees north. And we just found the total force on a charge that is in a two-dimensional system. It seems like a lot, but again, the basics here are using Coulomb's law to get the two charges, to get the two forces, and then adding the two vectors using vector components. So there'll be some practice questions given to you, some textbook questions as well. But good luck learning Coulomb's law. If you have any questions, don't hesitate to email.